Good evening, guys. So I hope you're able to hear me, right?
Yes, sir.
Yeah. So positively, we should be done with this chapter by today. Let's get started. So yesterday we discussed an important point about intrinsic and extrinsic semiconductor. And in extrinsic semiconductor, we saw two types which were called as P-type and N-type semiconductors. Is that right?
Yes, sir.
Right. Now what we are going to do is, we'll go to the next topic, that is the application of these P and N-type semiconductors. The first application takes place in a device called as a PN junction diode. Okay. So generally here, the first point I need to mention is how a PN junction diode is actually formed. If you take a single crystal, right? Generally, what misconception people have is they take a P-type semiconductor and N-type semiconductor and they merge them together to get this PN junction diode. But actually what happens is, if you take a single crystal of germanium or silicon and one side you divide it and make it as P-type and the other side you make it as N-type by doing the right level of doping. Okay, if one side of a single crystal of a pure semiconductor is doped with acceptor impurity atoms and the other is doped with donor impurity atoms, then we can say a PN junction diode is formed. Okay, sorry, actually a PN junction is formed. Let me explain what happens in this case. So we know that P region, that is this side, has excess amount of holes and this side has excess amount of electrons. Okay. Now what happens? As soon as this junction, that is this border is formed, there are free electrons that are present on the N side and holes that are present on the P side start moving towards their opposite ends. Means the holes that are present here will start moving this side and the electrons that are present here start moving this side. Okay. And why is this happening? It is happening due to but it is happening by the process of diffusion. And the logic is very simple, because if I take something like this, at this junction, you have this P-type and you have this N-type. When these two charges are close to each other, virtual positive and the negative charges are closer to each other, then what happens is this negative charge and the positive charge merge together, right? So what happens when the negative charge starts moving this side, then we can see that there is a vacancy created at the place where there was negative charge initially present. Then that becomes a hole and this becomes negatively charged. Okay. So this is the first step. Are you guys clear with what I mentioned now? This is a very, very important point. Are you clear with what I mentioned?
Sir, can you repeat this part?
Yeah. So what I'm trying to say is, listen. This is the junction. Right side of the junction, you have negative charge. And on the left side of the junction, you have holes. Right? When the virtual positive charge and negative charge are closer to each other, what will happen? When there is a positive and negative charge closer to each other, what will happen?
They attract each other.
They attract, right? So the electrons start moving from the N side to the P side. They get diffused naturally. This is a naturally occurring process. Nobody is forcing it. Okay. When that happens, then there is a loss of electron on the right hand side. So which will be a hole accepted. Now, what will happen to this one? This hole will become neutral. This hole will become neutral. So when it is neutral, there is another electron here. This electron starts moving here and there is a hole that is formed at this point. Now, when the electron moves here towards the hole, it becomes negatively charged, and this negative charge will again start flowing to the other neutral part. Then there will be a small amount of negative charge. See, on the P side, you're able to observe this. On the P side, what happens is there will be a small amount of negative charge that is getting generated due to the natural flow of electrons taking place from the N side towards the P side. And it is happening by the process of diffusion. So this kind of a merging takes place, and this kind of a negative charge will get generated at the end of P junction. Okay. As a result of which, what will happen? There will be a slight amount of positive charge that will exist on the right of, on the left of the N junction or the right of the P junction. So when this kind of an opposite polarity is going to get generated, this will stop the further flow of electrons from the N side towards the P side. Okay. So are you able to understand? Do you need any other explanation? I'll give.
Clear, sir.
Convinced, right?
Yes, sir.
Yes. Yes. Okay. So this junction, at the junction, there is a kind of barrier that is formed. And this barrier is what is called as a depletion layer. So in this depletion layer, what happens is, since there is a small amount of positive charge on the right hand side, what we can do is we can say that there is a virtual positive charge present. Let's say it's not virtual, actually it is a positive charge. And here I can say that there is negative charge present, and there is a small amount of potential difference developed. And this potential difference is what is called as the barrier potential. And why is this barrier potential occurring? Is it happening naturally, or is it happening because we connected some external device to generate something like this?
Naturally, sir.
It is a naturally occurring process. Am I right? So remember this word barrier potential. Now, see, let me read out. Okay, I will mention the story, but let me read out. So during this process, the electrons crossing the junction from the N region into P region recombine with holes in the P region very close to the junction. That is what I mentioned. Right. Similarly, holes crossing the junction from the P type into the N type region recombine with electrons in the N region very close to the junction. Now, what will happen is, there is a region which does not have any mobile charges very close to the junction. This is what is the region where there are no mobile charges, because what will happen when there is a negative charge developed here, when the electron tries to go towards the P side, these electrons which are already present near the P junction will start repelling the electrons. Okay, then this forms like a barrier. It's like a small dam that is created, and that region is what is called as the depletion region. In this region, what happens is, on the left side of the junction, the acceptor atoms become negative ions, and the right side of the junction, the donor atoms become positive ions. Okay, as a result of which, there is an electric field that is set up between the donor and the acceptor ions in the depletion region. Okay, now what we can say is, the potential at the N side is higher than the potential at the P side. Okay. Now what happens due to this? Therefore, the electrons in the N side are prevented to go to the lower potential of P side. Similarly, the holes on the P side find themselves at the lower potential and are prevented to cross the N side, due to which the barrier at the junction, which opposes the movement of the majority charge carriers, takes place. Okay. And the difference in the potential that is existing here is what we call it as potential barrier, or you can say barrier potential also. So generally, if you take the barrier potential, it is 0.7 volt when you use a silicon crystal, and it is 0.3 volt when you use the germanium crystal. Okay, and the distance from one side of the barrier to the other side is called as the width of the barrier, which depends upon the nature of the material. This is an important point to be noted. Means they are trying to say that the depletion region has some amount of thickness, and this is called as the width of the depletion layer. Okay, but the width of the depletion layer is in terms of few micrometers or nanometers. It is that small. Okay. Now, guys, am I clear with the basics? Is there any
Yes, sir.
doubts you want? Yeah. So this is a very important knowledge, because once you understand this PN junction diode, it's the same story for all of the diodes that we are going to talk about. Okay. Now, having said this, the next topic that we are going to talk about is forward bias PN junction diode and reverse bias PN junction diode. But before that, I need to mention what is biasing. Please make a note of this first. So biasing is something like this. Any semiconductor device connected across a battery through a resistor. So any semiconductor device connected across a battery through a resistor is called biasing. Okay. Right. So basically what I'm trying to say is, you take a semiconductor device. Let's say you take a PN junction diode itself, and you take a resistor, and through that resistor you connect it to a battery. Then you can say that this PN junction diode is biased. Whether it is forward biased or reverse biased, that's a different story that we will discuss later. But you have to understand one point here. This is an external battery. Okay, this is an external battery, but across the PN junction diode, there is a potential that is created, right? That is not external, that is happening internally and naturally. It is a naturally occurring process. Am I clear with this? There's a very, very important point to be noted here. So this will also, the barrier potential will also exist. Along with it, you will be connecting an external battery also, okay, to do some kind of changes to that particular device. Clear, guys?
Yes, sir.
Very good. So, forward biased, as the name suggests, right? If a PN junction diode is connected to a battery in such a way that the P type of the semiconductor is connected to the positive terminal of the battery and the N is connected to the negative terminal of the battery, then this type of a connection is called as forward biased PN junction diode. I'll tell you why it is forward biased, because the diode has two important properties that it exhibits. One is it can behave like a conductor and it can behave like an insulator also, depending on how you connect this particular battery. Okay, so let me explain how it is happening. Listen to this very carefully. Okay, if I take this positive charge, see, one thing that has occurred is the P type, the holes started diffusing to the right and the electrons were getting diffused to the left. So this was a process that happened naturally. Now, the process got stopped due to whom? Can you guys tell me? It is because of the, yeah, very good. It is because of the barrier that is formed. Barrier is like a dam. Right? There is something obstructing this kind of a natural phenomenon. Now, what we are going to do is, if you are going to use the external battery in order to ensure that this diffusion process is not stopped and the process gets carried on smoothly, then you say that this is a forward bias connection. Means what should happen? Logically tell me, if these holes, right, if these holes which are there on this side, if you expect them to move to the other side smoothly, what is supposed to happen to the barrier? Is it supposed to break or is it supposed to become big? Is it supposed to break? See, logically tell me one thing, guys. There is a wall, okay? And you have a ball on this side and you want this ball to go on the other side. How can you do that? Only if you break this wall. You need to break it. So that wall that I'm trying to talk about is the depletion area. So what I'm supposed to do is, remember, the depletion region already has a potential in this way. This is positive charge, this is negative charge. Now what we are trying to do is, you are applying a positive charge against the positive charge of whom? Against the positive charge of the barrier potential in such a way that the hole that is there, right? So the hole that is there will be repelled due to this positive charge of the external battery, and the hole will start moving to the other side by making this barrier potential a smaller one. And similarly, what will happen? The negative charge that is present here will repel the already available negative charge on the inside, and these electrons will start moving to the other side. As a result of which, what is happening? There is something called as recombination that is taking place. That is, the holes and the electrons are able to recombine with each other. If this kind of a phenomenon occurs in a semiconductor device, then we can say that particular device is conducting. Okay, so in this case, what is happening? The PN junction diode is perfectly behaving like a conductor, means its resistance is going to be very, very less. Right? Does that make sense? Yes?
Yes, sir.
Right. Now comes an important question. See, generally, before you connect this battery, right? Let's say you're starting at 0 volt. When it is at 0 volt, we know that if it is a silicon semiconductor, the potential barrier has 0.3 volt. If it is a germanium conductor, the potential barrier is 0.3 volt. Now, initially, before you connect this external battery, the potential that you're applying to the PN junction diode is going to be 0. Now, let us assume that it is made up of silicon. Then tell me logically, what should be the minimum value of the potential I need to increase from 0 to what value should I take it so that this barrier is completely broken? So if I start at 0 and the crystal is made up of silicon, what is the value I need to increase from 0?
0.7.
Very good. So the minimum value is 0.7. After 0.7, what is that you can say? You can confidently say that the barrier does not exist at all. Correct? So minimum value that you supply is what is called as the potential, is called as the knee voltage, which I'll come to that point. Okay. So I hope you understood what the story of what is happening behind a PN junction diode connected in a forward bias condition. Am I clear with that?
Yes, sir.
Now you guys tell me, when can I say it is in a reverse bias condition? So for reverse bias condition, P should be connected to which terminal and N should be connected to which terminal?
P to negative, N to positive.
Very good. So P should be connected to negative and N should be connected to positive. If this kind of a thing happens, see, the holes that are there, this side, the holes will get attracted to this negative charge and the electrons will get attracted to this positive charge, as a result of which the holes and the electrons will start moving away from each other. When they are moving away from each other, then what can I say with respect to the width of the depletion region? That will also start increasing. So when it is going to get increased, then what will happen? Will there be a flow of current taking place? Obviously not. So in this case, can I say it is behaving like an insulator? In this case, can I say that PN junction diode is behaving like an insulator? Yes or no?
Sir, can you repeat
Which one? Ma? Sorry.
why it becomes an insulator?
Because you have electrons here, right? This is N-type. N-type, what are the majority charge carriers? Electrons.
Electrons.
These electrons, tell me what would be their direction of flow as soon as you connect this battery. Will they move to the right or will they move to the left?
Right.
They move to the right, no? When they move to the right, that is this region, the amount of negative charge that is there, it will start getting diverted in the rightward direction. Then what will happen to the holes that are present here?
They move on the left.
They
Yes.
move to the left. As a result of which, what is happening is there is nobody to restrict There is nobody to restrict whom? The barrier potential. Because the barrier already has a positive charge here and negative charge here by default. Correct? So what will this positive charge try to do? This positive charge will try to push it in this way, and the negative charge will push it in this way. In simple terms, to tell you that they both are connected in such a way that they support each other. As a result of which, when the electrons are moving this side and the holes are moving to the left-hand side, there is no opposition taking place for the depletion region. So what will it try to do? It will naturally try to expand its region. Okay, it will try to expand itself.
Yes, sir.
Right. So when it is expanding, then what is happening to the size of the depletion region? It becomes very big. So obviously here our intention is not to make it conduct at all. Maybe that is also one of the uses of that particular device. Okay. So you can ask me a question, sir. In this case, you are saying it is going to act as an insulator. Is there any use of this device? Yes, there is a use. Because this phenomenon is used for something else. I'll tell you one of the applications is there. At that point, it will be useful. So the main advantage with a semiconductor is it behaves as a conductor in forward bias condition and it behaves as an insulator in reverse bias condition. This is the important point that should be stuck in your mind. If you understand this basic, everything else is easy. So if you guys give me a confirmation about this thing, so whole story which I told you, no, this will be here. When I share the notes after the chapter is over, you can revise it. That's not a big deal. Right? Now, one point that you need to make a note here is the width of the depletion region will increase. But the question is, can it increase for an infinite amount of time? The answer is no. It cannot happen. So the width of the depletion region will increase to a certain point, after which there will be a breakdown that has taken place. Let me explain what this breakdown is. Okay. If you take a capacitor, right? Positive charge, negative charge. In between the capacitors, what is placed? In between the capacitor, generally what you place? In between the plates of the capacitor, you will place a dielectric, correct? So, in this, there is a reason why I'm trying to speak about capacitor here. Listen to this carefully. So, this dielectric is there. Inside the dielectric, there is something called as polarization taking place. Because due to the positive charge and the negative charge on the plates, there is an external electric field present. And due to the induced electric field, there will be an electric field in the opposite direction. As a result of which, I can say that the charges have got polarized. You guys remember this concept?
Yes, sir.
Right. Now comes an important question. There is something called as breakdown voltage with respect to a capacitor. Can someone tell me what does it mean? There is something called as a breakdown voltage with respect to a capacitor. Any idea of what it is? At least do you remember this word? Breakdown voltage?
It is the maximum voltage a capacitor can handle.
Okay. After that, what will happen? After that voltage, what do you think the capacitor will?
To get damaged.
Okay. So that's what you understand from breakdown, right? But generally, breakdown in terms of physics means, see what is there inside dielectric, right? Dielectric is basically what? It's an insulator. So if you keep increasing the value of electric field or increasing the value of the potential, beyond a certain value, what will happen is, I will say that this insulator experiences a breakdown. Meaning of that statement is, the insulator starts behaving like a conductor. Means the insulator will suddenly start conducting, but it cannot be an exact conductor. It has lost its property of insulation, due to which it starts conducting, but a very, very, very less value of current. Are you able to understand what is the meaning of breakdown now? So the particular point after which any insulator starts behaving like a conductor is what we call it as breakdown. Did you understand what I meant?
Yes, sir.
Now, why I told this story is this depletion region is there, right? This depletion region is something similar to the dielectric. As the width of the depletion region is increasing, what will happen? It will have more amount of insulating property. Which one? The diode. The diode will have more amount of insulating property, but after a certain point, the depletion region can't take the value of potential that you apply. After which it experiences a breakdown and it suddenly starts conducting. But the question here is, when it starts conducting, is the value of current that is being conducted going to be high? The answer is no, because the conduction is taking place not due to the majority charge carriers, but it is taking place due to the minority charge carriers. Okay. So this is the reason. So I'm just read out. Let me read out. Since because of this, the large number of negative ions in the P region and there are large number of positive ions in the N region increases. Hence, the depletion region becomes wider and the potential barrier is increased. Since the depletion region does not contain majority charge carriers, it acts like an insulator. Therefore, no current should flow in the external circuit. Right? But in practice, what will happen is, practice means when you do this practically, you will observe one thing. I'm not sure if you have done this experiment in lab. When you do it, observe this, okay? But in practice, what happens is a very small amount of current of few microampere will flow in the reverse direction. And why is this happening? It is happening only due to the minority carriers which are flowing in the opposite direction. Happening purely because of the minority charge carriers which are flowing in the opposite direction. And this reverse current is small because the number of minority charge carriers in both the regions is very small. Okay. So this is what happens. Did you understand the difference between a forward bias PN junction and a reverse bias PN junction?
Yes, sir.
Right. Now I'm going to explain you something more important. With that, you will get a little more clarity on what I spoke about. So generally, if you take the symbol for a semiconductor diode, it is like a triangle with a line and two ends. And this end is going to be P end and this end is the N type. So this is the P type and this is the N type. Okay. Now I'm going to talk about forward bias characteristics. So when I say characteristics, it is basically a graph between voltage and current. Okay, wherever you see the word characteristics with respect to a semiconductor device means you're trying to see how the input value is changing the output value. Out of V and I, which is input value? You give input voltage and you get output current. Correct? So the circuit for the study of forward bias characteristics of a PN junction diode is shown in the figure below. See, if you observe, no, whatever we drew in the case of, this one, whatever we drew in the case of the forward bias PN junction diode, it is the same thing, except with the fact that since you're doing this experimentally, you need some measuring devices. That's it. Okay, so you take a PN junction diode, and this PN junction diode, when can I say it is forward biased? When P is connected to positive and N is connected to negative. If you observe, P is connected to the positive and N is connected to the negative. Okay, and this has happened through a resistor. If you see the definition of biasing that I gave you, you will understand it better. So what did I say biasing is? Biasing is connecting any semiconductor device across a battery with the help of a resistor. Right? So when this kind of a device is connected, then you will be using a voltmeter to measure the forward voltage and you will be using an ammeter to measure the forward current, which is IF and this is VF. Okay, and we know the fact that the potential source is connected parallel to the device and the current source is the device to measure the current is connected in series to the device. Is there any doubt in this diagram? Is there any doubt?
No, sir.
Okay. So when you do the experiment in the lab, right, you will have a small knob. You know what is a knob, right? That is the one, it will be like a screw where initially the value of the knob will be at 0. And from 0, you will keep increasing the value. When you keep increasing the forward voltage, then you can observe that the value of forward current will start increasing after a certain point. So that is, if you draw a graph between the forward voltage and the forward current, the first thing that you can observe is initially the current will be almost 0. But after a certain point, the current will start increasing suddenly, and that forward current will generally be in terms of milliampere. Can you tell me what is the point after which the current will start increasing if it is a silicon and if it is a germanium semiconductor? So what would be the voltage after which you can observe this kind of a change? This we have already discussed. What is it?
Greater than threshold frequency.
Sorry?
Threshold frequency greater than.
So for silicon, it is 0.7 volt, and for germanium, it is 0.3 volt. And this voltage is what we call it as knee voltage or cut-in voltage. So this, you are able to understand what I'm trying to say. So initially, when you start the forward voltage from 0 till you reach that value of 0.7 for silicon or 0.3 for germanium, the value of voltage that you supply will only be utilized to break the depletion region. Once the depletion region is broken, it becomes a pure conductor, and in that process, you can observe that there is a rapid increase in the value of current. Does it make sense? Are you able to understand what I'm trying to say? Okay, this experiment, I'm sure it will be there in your practicals. So when you do it practically, you will be able to relate to this concept better. Clear? Now, what did I say with respect to the reverse characteristics? So when I say about reverse bias characteristics, the connection is still the same, except the fact that the polarities of the batteries is reversed here. Okay, if you reverse the polarities of the battery, then you will have something like this. There is a reverse bias characteristic. So in this case, what is going to happen is, so can you tell me the steps that are occurring first? The width of the depletion region becomes wider. Second, after a point, what will happen? After a point, will the depletion region be able to sustain? After a point, the depletion region breaks. And then what will happen? Conduction happens due to whom? Due to the majority or minority charge carriers? Due to minority charge carriers. Correct, Ada? So is this not what is happening? So when the conduction happens due to the minority charge carriers, the reverse current IR is in terms of what value? Is in terms of few. In terms of few.
Microamperes.
It is in terms of few microampere. Unlike the forward current, which was in terms of few milliampere. Okay. Now this graph will make you understand. So initially you start at 0. Okay, voltage is taken along x-axis and the current is taken along negative y-axis. I'll tell you why it is taken like that. So when you start increasing the value of current, so when you start increasing the value of voltage, the reverse current is almost 0 till a particular value, beyond which what will happen is there will be a sudden increase in the value of current that is taking place. Right? There will be a sudden increase in the value of voltage that is taking place. And the value of voltage at which this kind of a phenomenon occurs is what is called as breakdown voltage. Now, are you guys clear with both the parameters? Where do you speak about cut-in or knee voltage? Cut-in or knee voltage is spoken in the case of
At forward bias.
In the reverse bias condition, what is the voltage you're speaking about? Where the sudden rise in current is
Breakdown
taking
voltage.
It's called breakdown voltage. Seriya? So remember this graph in the breakdown voltage. In the case of a PN junction diode, we can say that the current is going to be something like this. So current will increase when there is an increase in the value of voltage also. And this current is flowing only due to the minority charge carriers. Never forget this word. Okay. It is purely happening because of the minority charge carriers. So give me a confirmation. Are you clear with what is biasing, forward bias, reverse bias, and the
I have
characteristics?
a doubt, sir.
Please tell me.
So during reverse biasing, usually the diode acts as a insulator, right, sir?
During
Reverse biasing, the diode acts as an insulator, right, sir?
the diode, I'm not able to hear after diode.
Acts as an insulator.
Yeah, diode acts as an insulator, but I told you one thing, no. After a point, the depletion region breaks. And when the depletion region breaks, because any insulator in this world, beyond a point, it cannot sustain. There will definitely be a breakdown voltage.
But
Breakdown
that'll be
value.
very high, sir.
Which one? The breakdown voltage, no?
Yes, sir, it would be high, right?
It should be high only. I never told it is going to be low. Breakdown voltage will be high only. Okay. For which, when you do practically, you will understand things better. The knee voltage is somewhere around 0.7, right? It is very small. 0.7 volt for silicon and 0.3 volt for germanium. Whereas you will not get it in terms of fractions when you talk about the breakdown voltage. Okay. One thing I can tell you is when you're doing this experiment, make a note of this point and you come and tell me what value you're getting. It will be a very high value. You're able to understand? It will be a slightly higher value. Yeah?
Yes, understand.
Okay. Now comes an important question. So we understood that a PN junction diode can behave as a conductor as well as an insulator. Can this property be used in real-time application is what we need to know. Where the first application of a PN junction diode comes something like this. That is a PN junction diode acting as a device called as a rectifier. Okay. Before I explain what a rectifier is, let me explain this. Let me draw a block diagram. You have an AC main source, okay, and you have your mobile phone, right? Your mobile phone obviously has a battery which needs to be charged, correct? So if I ask you what is the logic as an end consumer, right? We are all end consumers. What do? We bring the charger, we connect the charger to the mobile phone and take it and plug it into the AC main source, correct? So this charger has an adapter here. This is where we need to raise a question. See, when I say AC main source, how much is the voltage we are able to generate? You are able to generate 230 volt AC source. There's an RMS value, that's a different story, but you're able to generate the 230 volt. Now, logically think, if you take the 230 volt and directly connect it to your mobile phone, do you think your mobile phone can survive? Do you think it will even exist? It will not even exist. It is going to blast, obviously, right? Because it doesn't need that much of value. The lithium ion battery that is there, it doesn't need that value. Now, what we are supposed to do is, and secondly, it needs to store the energy in the form of DC. Right? What does it need to do? It needs to store the energy in the form of DC so that there is a constant reduction in the value as time progresses. That is why you will have a discharge of battery taking place, for which again you need to start recharging the battery. Right? But here I have an important question to be asked. So AC source is coming here, but you're connecting it to a device which requires only DC. So what should be the intermediate process that should take place? What do you think is the intermediate process that should take place? The thing is
Conversion of AC to DC.
yes. So first thing is this AC value, which is 230 volt, has to get stepped down. So when I say it has to get stepped down, then what is the device you use for stepping down the value? Knowledge from your 7th standard. 7th chapter. It is a transformer. Then the transformer will give you what kind of an output? Step down AC value. So when you take the step down AC value, this we need to connect it across a particular device which can give us a DC output, correct? Then this device that comes into picture is what is called as a rectifier. And which is the device which can act as a rectifier? It is a PN junction diode. Did you understand what I meant? Are you guys able to understand the story?
Yes.
Yes,
Right.
sir.
So now what we are going to do is since we have the knowledge of forward bias condition and reverse bias condition, we are going to take that knowledge and apply it into a device called as rectifier to understand how it works. So if you take the process in which alternating voltage or alternating current is converted into direct voltage or direct current, then you call that process as rectification. And the device which is used for this process is what is called as a rectifier. So means I can take a PN junction diode and give a particular circuit in such a way that this kind of a process can take place. Okay. Let me explain how it happens. We know this, that the junction diode has the property of offering low resistance and allowing current to flow through it in the forward bias condition. And this property is what is used in the process of rectification. Right. Now, basically, when you talk about a rectifier, there are two kinds of rectifiers. One is called as a half wave, and the second is called as a full wave rectifier. Okay. So, if you talk about a circuit which rectifies half of the AC wave, then you call that as a half wave rectifier. For this, what will happen is this is the circuit diagram. I told you already, you need a transformer to do what? To step down the AC voltage. So, line voltage from AC power is taken here. Then it is connected through a step down transformer. We know that in a step down transformer, the primary windings are going to be more compared to the secondary windings. So through the step down transformer, you will be generating a voltage here. And this voltage will also be in the form of AC. Correct? But it is going to be a lesser value compared to the value that was present at the input. Right? Now, when I take an AC voltage, if I take one particular cycle, guys, if I take one particular cycle, I have positive cycle and negative cycle. So during the positive cycle, if I say P1 is positive and P2 is negative, then what will be the value or what will be the nature of the sign that is going to be present at S1 and S2 side? Then this will also be positive and this will be negative, except corrected. That's what the basic of transformer tells us. Am I right or wrong? So P1 is positive, P2 is negative. During which cycle? During the positive half of the cycle. Then, if this end is taking the positive sign, now look at the diode and look at the sign of the voltages which are connected to the diode, and tell me whether in this scenario is this forward bias or reverse bias. Is this forward biased or reverse biased? Guys, I need an answer. I asked a very simple question.
Forward, sir.
So it is
Forward bias.
correct. It is forward bias because P is connected to positive, N is connected to negative. Sharia. Now, this RL is there, no? This RL is called as the load resistance. See, load resistance will not literally a resistor. See, for example, at your home, when you switch on fan is rotating, right? That fan is called as a load. It is called as an electrical load. Similarly, when you switch on, the light is able to glow. That light is called as the load. So all these devices have certain amount of resistance associated with them. That is why we wrote it as RL. RL stands for the load resistance. Now what will happen is, in this case, since the PN junction diode is in forward bias condition, can I say it will act as a conductor?
Yes, sir.
Right. When it is going to be in the forward bias condition, then what will happen to the output occurring at the load resistance? Will it appear or not appear? See, forward bias is the conductor. There is a conductor. When it is a conductor, will you be able to see a load across the will you be able to see an output across the load resistance or not? Means if I keep an LED here, if I keep a small LED bulb here, will that glow or not? Tell me.
Yes, sir.
It will glow.
Yes, sir.
Right, because it is acting as a conductor. Means during the positive half of the cycle, I am trying to say that there is a load, that there is an output occurring across the load. Correct? Means the positive half of the cycle is allowed to flow through the PN junction diode and you are able to see an output here. Now, what about the reverse bias? What about the negative half cycle? Try to understand this. What will happen during the negative half cycle? So during the negative half cycle, this will be negative and this will be positive, correct? Because the polarities are supposed to get reversed. During the negative half of the cycle, this end will be negative, this end will be positive. See, it is not a thumb rule that every time this will be negative and the other will be positive. Since in the previous case, I assume this to be positive and negative. In the case of negative wave or the negative cycle, the polarity has to get reversed. If P1 is negative and P2 is positive, then S1 is negative and S2 is positive, correct? Now tell me, what is the kind of biasing the PN junction diode is undergoing? It is a
Reverse, sir.
reverse bias. What will happen? It behave like an insulator.
It'll act as
And
an insulator.
Insulator. So if you connect an LED, will it glow?
No.
That's means the negative half cycle that is coming from the AC source is cut off. Correct? Again, what will happen during the next positive cycle? During the next positive cycle, again it will conduct, and during the next negative cycle, it will insulate. And next positive cycle, it will conduct, and the next negative cycle, it will insulate. Are you guys able to understand this point?
Yes, sir.
Sir, I have a doubt, sir.
Yeah. So I hope this
Sir,
clear.
I have a doubt, sir.
Please tell me. Please.
Sir, the reason we use a step down transformer here is to reduce the voltage, right?
To reduce the AC voltage.
And the diode is used mainly to make it DC.
To convert. So this is AC. Try to understand. This is AC. Okay, as soon as this AC passes through this diode and comes out from this side, it becomes DC.
Okay, sir.
Provided in that scenario, the diode has acted as a conductor or an insulator. It depends on that scenario. Okay.
Yes,
Now,
sir. Understood.
okay, now I have an important point to take here. That is, during the positive half cycle, you are able to observe that the diode has conducted and you're able to see the output. Negative half cycle is cut off. Means out of the full wave that you have, only half wave has got rectified. That is the reason why we call this as a half wave rectifier. Are you able to understand this? So that's the reason why we call it as a half wave rectifier. Okay. Now, one more important point that I need to mention here is, I told you that DC is occurring, but you're able to see that there is a wavy kind of structure that is there. When there is a wavy kind of structure, how can I call it as DC? I thought somebody will ask me this question. Then how did they call this as DC, guys?
So variable DC, sir.
Perfect. It's called as fluctuating DC or unregulated DC. Because what is the basic definition of DC? There is a misconception that is there. Can you tell that also, Ma? Generally, AC is called as bidirectional current. And DC is called as
Unidirectional.
unidirectional. Now, is it satisfied? Means the current is restricted only to one side of the graph. That is the reason why I called it as DC. But the important point here is, it is an unregulated DC. So what I told you, right, about the charger example. Coming to that, the rectifier is giving us unregulated DC. Okay. So this can also not satisfy the whole condition. We got DC, that's a different story. But it is unregulated. But our mobile battery needs a regulated voltage. For that regulated voltage only, you will be connecting another device in series, which is called as a Zener diode, which acts as a stabilizer. It's called as a voltage regulator. We will be discussing about this, don't worry. But tell me one thing, are you clear with half wave rectifier?
Yes, sir.
Yes, sir.
Right. Now, if you see the half wave rectifier, its efficiency is very less. It's only 41% approximately. That will not be comfortable to use because half of the cycle is lost, means you are wasting half of the energy of a cycle. So in order to make the efficiency higher, we generally don't go with the half wave rectifier, rather we go with the full wave rectifier. So full wave rectifier, what it does is, the only difference is instead of using one diode, we will be using two diodes. And secondly, for the secondary transformer, you will have this kind of a connection, which is generally called as center tapping. Okay, the center tapping, what it does is, it will divide the whole circuit into two equal parts, where this is the upper part and this is the lower part. Okay, it divides the circuit into two equal parts. Are you able to understand this point? Right. So now see, you give an AC input. Listen, positive half of the cycle. Then what will be the polarity here? If this is positive, this will be negative. Accepted? Then what will happen at the secondary end? This will be positive and this will be negative. Now tell me logically, due to the positive charge in the upper end, the upper diode D1 will behave like, is it in forward bias condition or in reverse bias condition? It is in the, this diode D1, is it in forward bias condition or reverse bias condition?
Forward bias.
It is in a forward bias condition. So when it is in forward bias condition, this diode will conduct this positive half cycle, which will appear here. But what is happening to diode 2? The diode 2 being diode 2 being under reverse bias condition, it behaves like an insulator. So the positive half of the cycle is rectified by whom? by diode 1. Now, if I take the second, that is the negative half. If I take the negative half, then this will be negative and this will be positive. Then here what will happen? This will be negative and this will be positive. Correct? When this is happening, now what about diode 2 and what about diode 1? You tell me which one is forward biased and which one is negative, reverse biased. So which one is forward biased and which one is reverse biased?
In the next half cycle, sir.
No. Look at the diode 1 and diode 2. Which one is forward biased and which one is reverse biased? Only diodes are forward or reverse biased.
Diode 1 is reverse.
Diode 1 is
2
reverse, 2 is forward. So diode 2 will generate the output across the load. So this is for the negative half of the cycle. So this output is generated by diode 2 and this output is generated by diode 1. Similarly, the next half of the cycle, who will become positively charged? Like which one will become forward biased? Again, diode 1.
Yes, sir.
And again, in the next half of the cycle, diode 2 will become forward biased. So, with the help of two diodes and with the help of a technique called as center tapping, what are we able to achieve? Center tapping, what does it do? It breaks the circuit into two equal parts. Right? When you do this kind of a when you create this kind of a circuit and follow the procedure, then you're able to see positive half cycle and the negative half cycle both are getting rectified. So both are getting rectified and the full wave is rectified. That is the reason why we call this as a full wave rectifier. Okay, is that clear, guys? So we saw how a PN junction diode works as a full wave rectifier. Now the next concept that we need to see is the special types of PN junction diode, where one is Zener diode and Zener diode's application as a voltage regulator, then the special types of diodes. Okay, for which I will need maximum half an hour of time. I'll try to arrange a class.
So Zener diode is deleted, right?
Zener diode, I think it is not. Let me check once. Did they say it is deleted in school?
Yes, sir.
Okay, let me
Yes.
check. What about the other diodes, photodiode and all those things?
Those are there.
1 minute. Then just stay online, don't leave. Yeah, sorry, I didn't check it. Yes, it is deleted, yes. So then, see, actually what I thought is I'll explain Zener diode, then I'll give this LED photodiode and solar cell because there is nothing for me to explain. It is all theory part only, which you guys have to read. Okay, so what I will do is this LED photodiode and solar cell. This part alone, I'm giving it as self-study. Okay, because as I told you, there is nothing much for me to explain. If you read itself, you'll understand. Your work is only to read them and write it in the paper. So you guys read it, and if there is any doubt, reach out to me. Okay, so with this, can I take that the syllabus is over? Okay, can I say that the portions are completed? But don't worry, when I give you, yeah. So this part alone, you have to do a self-study. That's it. There's the only thing that I'm giving you, do a self-study. That's it. I'll be sharing this notes, go through it. Okay. First make notes, then start studying. Then if you have any doubt, reach out to me. Okay.
Thank you, sir.
Yeah, that's it.
Thank you.
Thank you, sir.
Thank you. Thank you, sir.
Yeah, you guys can leave.